Đấy, thì hôm nay chúng ta là rất vui mừng là đón được nghe thuyết trình của giáo sư Lưu Trần Trung. Đấy, thì từ trường Đại học Hồng Kông. Có thể nói qua một chút về Trần Trung. Thứ nhất là về mình với Trung đã quen biết với nhau từ rất lâu rồi, hơn 20 năm rồi. Thì Trung với mình là học cùng lớp cấp 3 với nhau, mà không những cùng lớp cấp 3 mà còn ngồi cùng bàn với nhau khoảng 3 năm. Nhưng mà tuy nhiên là mình với Trung lại chưa gặp nhau cũng từ sau khi mà kết thúc học cấp 3. Tất nhiên là hai người vẫn luôn luôn theo dõi nhau trên cái hành trình khoa học. Thì Trung thì sau khi mà học hết cấp 3 thì học cử nhân tài năng ở trường Đại học Khoa học Tự nhiên, và sau đấy thì có nghiên cứu một thời gian trong nhóm của thầy Nguyễn Thế Bình ở khoa lượng tử của trường Tự nhiên. Và rồi thì Trung thì chuyển sang Hàn Quốc làm master, và một cái quan trọng là sau đấy cái bước chuyển quan trọng là sang Max Planck Institute của Đức để mà bắt đầu làm PhD và về hướng là về về attosecond laser, và rồi tiếp tục làm postdoc ở trường ETH ở Zurich, một trường đại học cực kỳ nổi tiếng của Thụy Sĩ. Và hiện tại thì Trung thì là assistant professor tại trường Đại học Hồng Kông. Thì nó qua một chút về quá trình nghiên cứu của Trung. Đầu tiên là Trung thì khi mà bắt đầu ở trường Max Planck thì có tham gia vào làm cái gọi là synthesis ánh sáng để mà tạo ra được từ những cái bước sóng khác nhau tạo ra được xung cực ngắn attosecond laser, có thể nói liên quan trực tiếp đến giải thưởng Nobel cách đây vài năm và một vài công trình quan trọng của Trung có rất nhiều publication nổi tiếng, nhưng mà có thể nói là có hai cái paper mà mình cảm thấy là gọi là breakthrough, là tạo ra được extreme ultraviolet, là bước sóng siêu ngắn ultraviolet và thì có tầm đến vài chục nanometer. Thì là bằng cách là high harmonic generation và chiếu laser ở bước sóng dài, sau đấy nó chuyển thành bước sóng cực ngắn, và lần đầu tiên quan sát được ở trong vật liệu solid, vật liệu chất rắn, by Nature. Nói chung là first author vào năm 2015, hiện nay là đã cite đến hơn 700 bài. Và sau đấy thì cũng là có, vì trước đây thì cái extreme ultraviolet high harmonic generation này chỉ làm được ở gas thôi, chưa ai làm được những vật liệu khác. Thì chung là mọi người biết là có 3 trạng thái là chất lỏng, chất rắn và chất khí. Thì trước đấy là phải làm chất khí, thì nói chung là làm được by Nature là về chất rắn, và by Nature Communication là về chất lỏng. Như là ngoài tại sau, tất nhiên là sau khi mà tạo được cái nguồn source rồi thì đem đến nghiên cứu và xem là nghiên cứu vật liệu tính chất light matter interaction có gì thú vị khi mà mình đem cái attosecond laser để mà excite. Thì nhìn chung là sẽ có tiếp rất nhiều những nghiên cứu khác. Gần đây thì có một cái bài mà mình rất là thích, bởi vì mình cũng làm về vật liệu topo, tức là đo được cái Berry curvature của solid và sử dụng cái ánh sáng mà chúng nghiên cứu ra. Còn tất nhiên là Trung với mình thì gần như là trong 20 năm rồi chỉ theo dõi nhau từ xa, và bây giờ gần đây thì hai bạn đã bắt đầu nói chuyện với nhau, và rất là gần như là hầu như tuần nào cũng trao đổi với nhau để xem là có thể hợp tác gì với nhau không. Và có một cái mình rất thú vị với Trung, riêng mình thấy là hai bên mặc dù nghiên cứu thì rất là khác nhau, một vài điểm chung, một khi mà Trung mà nói chuyện với mình bao giờ cũng giảng giải cho mình một cách vô cùng là dễ hiểu. Mỗi lần là kết thúc câu chuyện với Trung xong mình cảm thấy mình thông minh hơn rất nhiều và hiểu rất nhiều việc, và cảm thấy wow, hay quá, mình có thể lại làm cái gì mới đây. Thì hy vọng là trong cái buổi nói chuyện hôm nay thì Trung cũng sẽ có thể, mình tin rằng là sẽ giới thiệu cái vấn đề nghiên cứu của mình cho mọi người, và bạn có thể là sẽ inspire được các bạn. Có thể sau đấy đi các bạn có thể có những cái collaboration với Trung như là mình đã bắt đầu tiến hành. Thì bây giờ xin mời Trung.
Cảm ơn Hải Sơn và xin chào mọi người, chào các thầy cô, anh chị và các bạn. Mình rất là vui khi mà được mời để give một cái talk này. Thì mình cũng hy vọng mọi người thông cảm, là bởi vì mình cũng không biết nhiều về terminology trong Vietnamese, thì mình sẽ chuyển cái talk này sau cái vài lời giới thiệu này thì mình sẽ chuyển sang tiếng Anh. Thì hy vọng là mọi người thông cảm, và nếu có vấn đề thì mọi người cứ hỏi cả tiếng Anh cả tiếng Việt. Nếu mà mình trả lời được tiếng Việt thì mình sẽ trả lời, mà không thì mình sẽ trả lời bằng tiếng Anh vậy. Thank you very much for the invitation for the talk, and it would be my great pleasure to discuss with you my personal journey to attosecond science. And I have to emphasize it is my personal journey because, of course, attosecond science nowadays have been kind of a big community, and therefore there are so many perspectives as how one can do this and how one can pursue science at the extreme limit of the time scale. And yeah, I understand it is quite a challenge between the time scale for all the speakers. So I hope that I hope that you will not be very bored and of my talk. So please just raise your hands or just unmute and ask me question anytime. I'm fine in any case, right? So yes, let's start. So first of all, I just have a very quick slides on my journeys, and Hai-Sơn already said before. And I did high school in chuyên lý tổng hợp with Hai-Sơn, and then I did my bachelor degree in khoa học tự nhiên Hà Nội, and then I moved to South Korea for a master degree, in Germany for PhD degree in physics in Max Planck Institute of Quantum Optics in Munich. And then I moved to ETH Zurich for my postdocs, where, it is kind of, it's a famous school where, Albert Einstein and other famous physicists work there. But of course, we have to get inspired by this famous scientists, and of course, we try our best. And at the moment, I'm taking up an AP position, so assistant professor in University of Hong Kong. And we set up our lab now with 2 postdocs, 6 PhD students, and some masters and undergraduate students. And we have a new opening. So please have a look at the last slides of the talk if you are interested, or please advertise to the relevant candidate, please. So I would divide my talk into few sections, and in the first sections, we're gonna talk about the very fundamental definition of questions. What is attosecond science? So let's start with the very basics, discussions on ultrafast technology and the birth of ultrafast technology. So here, as some of you might know, that Leland Stanford was the governor of California, and he was working together with my branch to really do one of the very first high-speed photography. And at that time, people was asking the very simple question whether do all the 4 hoofs of a trotting horse ever simultaneously leave the ground? Because at that time, it was not possible to really see that, and that the human, the speed of the human visual system is at the order of 10 to the 1/20 of a second, and that's why the movies frame rate was set up at 24 frame or 30 frame per second, because that is higher than the speed of the total visual system of the humans. So at that time, they was about to do high-speed photography, but at that time the time is limited, more like 40 milliseconds and up to maybe 20 milliseconds or so. But that was already enough to see that certainly there were some moments where all the hoofs of the trotting horse leave the ground. Just a side information, Leland Stanford was actually the generous donor who break the ground for Stanford University. So afterward, fast forwards, before the World War II, and then after World War II, there was quite a stint of fast developments of what is called strobe photography. So in order to capture very fast motions, people make the flash line that is extremely fast, so that with the flash burst of light, people are able to shine on any physical phenomena or dynamics, and then take the photos and capture the motions. And here you can see Harold Egerton in MIT demonstrated how to make an apple sauce. And you see that the bullets are extremely fast. But by having the light shots, the light pulse is as short as milliseconds, people can really make like a frozen image of a bullet bursting through an apple that you can see, right? And nowadays it is much easier to do, with standard photography techniques. People can do, as you can see, like the splashing image of a milk here over. So nowadays it is very easy to make a strobe photography. But of course, that depends on how fast you can make your light burst. Here, it has been summarized generically, so it's not precisely correct, these numbers, but you can get the idea of the scale. That the speed of the electronic has evolved over the years, but so far it's not really easy. There is no fundamental breakthrough yet for people to get electronics getting faster than this time scale, like 10 to the 12 minus 12, so like picosecond time scale. It's almost at the fundamental limit of electronics. However, with optics, the story is quite different, because with optics, because the fundamental frequencies of light is at the order of 10 to the 12, so petahertz frequency, it makes it rather easy for optics to go to faster time scale and higher repetition, higher frequencies. And here I just take out the reference from a review paper where it has shown, actually this review paper from my advisors. So it has shown that there was quite some notable work showing the developments of very short light burst. And most of them, actually, you see, is most of them got a Nobel Prize for the development related to this light source and the interaction, you can see. And very recently, you have the Whale, and then afterward, you will see that there was the Nobel Prize awarded to Zera Moreau and Donald Strickland, which I will discuss a little bit later today. And the center to this is that in order to make very fast light bursts or very short light bursts, people would need to make a very broad spectrum and then combine them in what is called a synthesizer of light, or the piano of light. Instead of having a piano of sound, you can have a piano of light. And then with that piano of light and the good enough input, you would be able to make almost on-demand laser pulse shaping and manipulations of laser pulses, almost on demand. And here I would like to show you kind of a visual videos on what is exactly the time scale. What is 1 attosecond? And it was made by my former laboratory. So you know that the distance between the moon and the earth is at the order of 300,000 kilometers. So if you count that distance for light, it is nothing but roughly 1 second of propagation of light. And correspondingly, if you compare the distance from Reims and Paris, it is only at the order of 1 millisecond. That how much time would take to travel between these two places. And fast forward, if you also take a shorter distance like 300 meters, light will only need 1 microsecond to go through. And now, if you look into further, smaller and smaller time scale, or shorter and shorter distance, you will see that light will only need, like microseconds. And then eventually, for example, if you look at the paper's box, then light only needs around 1 picosecond, which means 10 to minus 12 of a second just to pass through this. And we go further into picosecond time scale, which is femtosecond time scale, which is 10 to the minus 15 of a second, which is more or less the thickness of the given bacteria. And you see that it's need only around 1 femtosecond. Now, if you break down the given organics, any given living organisms, you will break it down into molecules, and water is a very abundant molecules. And you see that we are talking about very extreme time scale, where we're talking about 1 attosecond is a time it takes for light to travel around to travel along the size of one molecule, which is extremely small. And here we are talking about this time scale, where exactly this time scale that would allow us to understand how precisely the electron is moving inside one atoms or molecules. So in short, attosecond science is a branch of science that investigates dynamics, but in the attosecond time scale. And you can see that in another picture that in order to investigate progressively faster time scale, you need better or faster and faster laser pulses. And you can probe from protein motion, proton transfer, rotational, vibrational motions, and then finally electron motions. But in order to have extreme confinement of the electric field, Fourier transform tells us that we need very broad bandwidth and also coherence at the same time. And then together with the combination of nonlinear optics, we would be able to make very, very short laser pulses. But at the same time, we need the laser pulse to be very intense, because you need it to intense to activate nonlinear optics, to activate the frequency mixings that allows you to make different photons and photon energy from different photon energies. That concludes the first part of my talk, where I talk about the fundamental definition of attosecond science and what is attoseconds. Now we will go to the practical part, where we will discuss how one would be able to generate optical attosecond pulses, and then how one would be able to use these attosecond pulses to probe the nonlinear response of bounds and electrons. So here I quote, Hysen's and also my former slides where I talk about the Nobel Prize in Physics in 2018. So this was awarded for their developments of the technique which is called Chuff pulse amplifications. So, and in essence, their inventions were the demonstration of the techniques that allows people to make about 10,000 times more intense laser pulse that otherwise would not be available with their techniques. And the idea is simple. In order to overcome the damage threshold of the gain medium, they stretch the laser pulse first, and then they send it to the amplifiers, then they amplify it, and then after they get this very highly energetic and long laser pulse, they send it to the compressor. And then after that, you can imagine all the energy accumulated in the long duration in time is compressed to the very short time duration. Then you have the very high peak energies. And that's how people make the most energetic laser pulses nowadays still. So it is still more or less the technology, the state-of-the-art technology for now. And what happened if you shoot these laser pulses on a given materials, and of course people already tried this more than 30 years ago, where the moment they get these very energetic laser pulses, people, they just say, okay, let's do an experiment. We shoot it on what? We shoot it on gas, because gas is where it's, you can break things down into simpler terms and components, and that's helps people to understand it's, the easiest way for people to understand. But then even though at that time, when people shoot intense laser pulse on the gaseous media, they see something that they would not understand yet, which is the emergence of the many orders of the harmonics. And afterward, it is called high order harmonic generations. And people understand, okay, there was a principle for that. And Paul Cochrane in 1993 proposed a model which is called three-step models. And these models serve very well to explain the principle behind high order harmonic generations. So in short, I can explain to you as follows, that in the beginning, before the arrival of the main laser pulse, you only have the weak link of the electronic wave packet around the core due to the perturbative and pre-pulse. But when the main pulse come in, it will bend the potential strongly so that it allows tunneling. And in other words, it means that a part of the electronic wave packet would be able to release to vacuum. And then once it is released in vacuum, it will be driven by the modulating atomic potential plus electric dipole. Then it will be driven, or we call acceleration or propagation in free space. And there would be some probability for this electronic wave packet to recollide back to the parent ions. And that step is called recollisions. And the accumulated kinetic energies may allow the generation of the high energy photons. And that is the main step inside the 3-step modus. So here we will show you a simple animations to show you how does it look like an experiment where one would be able to generate an attosecond pulse trains. So this is a vacuum apparatus to detect the XUV. And the experiment is follows. In the beginning, you come in with a laser pulse, as you can see over here. And then you will shoot onto the gas target. And the gas target is nothing but this nozzle that is actually burned by the lasers. And if you zoom in the nozzle, you will see all the atoms and molecules, right? And regardless of whether it is, atoms or molecules, you can simplify the microscopic response as follows. Depending on the instantaneous electric field, the polarization response of the mediums will wiggle. How much is wiggle back and forth and evolve will depend on the strength of the electric field. If the strength of the electric field is very strong, it would allow release of a part of the electronic wave packet to the vacuum. And afterward, during propagation, there is probability for it to recollide back to the parent ions. And the moment of recollision back to the parent ions may allow the generation of high energy photons. And it is how high energy photon at the form of the high order harmonic generations is generated. And if you look into the macroscopic picture, where you look about an ensemble of atoms and molecules, and you will see that due to the precise synchronizations between the main pulse and the XUV, you will have a macroscopic build-up of XUV light. And this is exactly how attosecond laser pulses trains was made before. And here I will show you, okay, the apparatus to measure it, because, when you make something that is extremely short, you have to show them that you also measure it. Because without measurement, you cannot claim that you have made it. And one of the ways to measure it is called attosecond streaking. The technique is rather involved. I would just tell you in short that it is nothing but a time-resolved spectroscopic measurements. And by looking at the photoelectrons and by looking at the delay between the XUV pulse shown as a red line here and the IR pulse shown as the red, the violet and the red line here, you will be able to see the delay as a function of time. And by looking at this delay axis, you know that this laser pulse is extremely short. And in order to capture this laser pulse, you need something that is even shorter, which is this XUV pulse. And with proper mathematical reconstruction, one would be able to reconstruct both the XUV pulse and the IR pulse. So now, let's go back to our synthesizer of light. How do we make it? I show you how we generate it, how we measure it, but let's go back. How do we make it? We make it by having 3 components. So first of all, we need to make very broadband light source. And in other way, you may hear that when people talk about supercontinuum or rainbow, it is more or less what we did. But the difference between the rainbow and what we have is that the rainbow is what you see as a perspective from your eyes, but we do generate in our lab a supercontinuum spectrum, a very broad spectrum, and coherent light. And by having this coherent light source and we have the synthesizer, which is nothing but the piano of light, as I explained to you. We are able to manipulate different color differently. We can command the amplitude and phase or the delay of different color differently. And by doing that, we are doing nothing but Fourier synthesis. And this Fourier synthesis allows us to manipulate the electric field. And in this case, the electric field might be able to be confined to half a cycle. So think about half a cycle of the carrier wave of, let's say, 600 nanometer as the order of like 2 femtoseconds. Half a cycle of that is like 1 femtosecond or less. That is exactly the time scale we are talking about. And this broadband light source is nothing but the supercontinuum generation using the third order nonlinearities. So we would be able to explain to you a little bit deeper, but you just need to know this concept that when you shoot an intense laser pulse on a given material, then this given material would be able to induce a response. It will react, right? It will react to this nonlinear light, a very strong light, and when it reacts to this strong light, it will make its own electric currents, and in turn, it will make new light frequencies. And that's exactly how supercontinuum works. And we were able to make light, coherent light source, and very intense, and going more than 2 octaves. So it served like from roughly 270 nanometer to more than 1000 nanometer. And then we send that very broadband and coherent and intense light source into the light synthesizer or the waveform synthesizer. And what we're gonna do here, we will show you another animations where the input pulse is coming in, and then it will divide it, you can see here, it will divide it into different channels, and each of these channel will have its own amplitude and phase modulation. And by having this individual amplitude and phase informations, we can manipulate different colors of light. And after we manipulate them on demand, we can put them all back. The moment they are all back in space and in time, that is a moment where Fourier synthesis is done. And that is how one can make arbitrary waveform, almost arbitrary waveform. And in this case, you can see half a cycle later pulse. Now, one can say that, okay, this is what you draw on the picture, but can you tell me the measurement where you really show this? Because, I mean, if you draw on this picture, I can draw whatever I want, right? But we will show you that, no, we really measure it, and we prove scientifically that we have made it. And how do we do that? Of course, we use this piano of light. Just simply like, okay, you need a piano of light, and then you need a detector. And this detector would allow us to decompose the amplitude and phase. Just think about this detector is like, your ear. It already have some, frequency analysis inside, plus your brain. Then with that, you would be able to decompose into different amplitude and phase. And then what we're gonna do, we will do the feedback. And by doing multiple iterations, like a loops, maybe a few times, then we would be able to correct it. Or like if you say you are performing a score, but then you recognize that your ears hear that, oh, it's wrong, then you can correct it back. And this is exactly the same principle we are doing here, not with sound, but with light. And by doing that, we were able to really make a good feedback and roughly or almost perfectly control the amplitude and phase of individual colors. And once we can do that, we can really make a laser pulse that is effectively confined to only half a second. And that's exactly what makes our laser pulse, what we call optical attosecond pulse. And it is way more advanced than the XUV attosecond pulse that people generate, 30 years ago. And finally, we were able to make very high pulse energies and also, of course, half a cycle later pulse. And then the next thing people would ask is that, okay, Trung, you know, you can make it, but what do we do it for? Now it is for basic science. What we do it for is that we will use these laser pulses, you know, as short as attoseconds in order to investigate something equivalently short. And that something equivalently short is how fast a bound electronic wave packet react to incident light. You know by perturbation theory that it will react. You know by fundamental quantum mechanics that you can write down the polarization response very nicely. But would we be able to measure it or to follow it using experimental techniques? And that is how we will answer this. So we shoot our lasers on to the krypton target, and then we change the intensity of our lasers, and then we will scan the phase of our laser. So by changing the phase of our laser, we will change how the evolution of the laser pulse behave. So by changing that, we were able to record, and then with a proper mathematical model, if we are able to reconstruct this using a given mathematical model, then this mathematical model would allow us to extract some information. And this information is nothing but what is called a proposed delayed response of the bound electrons. Or in other words, we say that our measurement might constitute the first observation of non-instantaneity in bound electron response, which is not contradicting to quantum mechanics, but it is really the direct consequence from quantum mechanics, but it is usually overlooked when people look into longer time scale. So our tools allow us to look at the very fundamental foundations of quantum mechanics and how light interacts with matters. And we will show you here another videos
to see how quickly electrons would respond to these extremely fast flashes. The scientists illuminated atoms of krypton with optical attosecond pulses to set electrons in motion. These electrons are shown here as a green cloud around an atomic core. The physicists then measured the ultraviolet radiation of the wiggling electrons emitted in a vacuum. They repeated this experiment many times, each time with an optical flash, which applied a slightly different but precisely known force to the krypton electrons. From their measurements, they concluded that electrons take approximately 100 attoseconds to react to forces of light. These new findings comprise the first measurement of the response time of electrons on the atomic scale, with the results now being to see how quickly a scientific journal in Nature.
Okay, so that concludes the second part of our talk. And now we will go to the third part of our talk, where in this first part, in the second part, we discuss with you on light-matter interaction, where we only talked about matter being gases or gas medium. In this case, we will talk about how we're gonna do high-order harmonic generations and the spectroscopic applications, but in this case of condensed matter and specifically for solid. So as Hai-Sen already said before, you know, people have done light-matter interaction, I mean strong light-matter interactions in gases long ago, and then before our works, there were actually two other works, one from Stanford group in 2011, where they propose, which they show high-order harmonic generation from zinc oxide, and then there was a German group who show high-order harmonic generation from gallium selenide. But this work is as a mid-infrared regime, and this work is in the terahertz regimes. So then after seeing this publication, we ask ourselves, okay, is this possible to make it in the XUV regimes? And this is exactly you know, the question we asked, and we set out to do the experiments. And after some time, it turned out that, oh, it works. So there is something like that. And we published it. And then soon afterward, there were so many other publications. But essentially, all the papers that I show you here are more or less one of the first who really show that one can shoot very intense light on matter And you would be able to make a high order harmonic out of this. And here, just to have it, just to quote a sentence from Arthur Shallows and Ted Haynes, both are Nobel laureates, and they say that anything will lace if you hit it hard enough. And now we say that you can make any high order harmonics from any materials if you hit it hard enough. So let's go to our experiments. In our experiments, we have this half a cycle laser pulse, but of course we don't have to use that. We can use any laser as we explained to you. We have this laser pulse, we shoot on the materials. In this case, it is just few silica thin film, but actually this film is as the order of nanometer. So it's also kind of a delicate experiment because you have to handle nanometer, freestanding, no substrate involved. And you shoot it with very strong laser pulses. And then we detect the spectrum, XUV spectrum. Then by doing the measurements of our laser pulses, we know precisely what is the waveform or how the oscillation of the light wave is involved in our measurements. And then we also know the spectroscopic response, in this case in the XUV domain. And now if we increase the electric field strength, then we will see that the spectrum will also change. And this would allow us to get a dynamic response of the medium. So then by increasing the electric field strength, we will get a lot of spectra, and this spectra precisely corresponding to different input electric field strength and shape. And with this, we also measure not only high order harmonics that you can see here, we can also measure the cutoff energies as a function of peak electric field strength. And then we see that it is not really following the model that people known so well for gas before. And then we would have to ask ourselves, okay, then how do we represent it? Because this doesn't match what we understood before for gas. And one of the experiments one can do is to do semi-classical simulation where maybe I can talk about this a bit briefly. So if you want, we can discuss in detail. But now just to say, we have a conduction and a valence band. And then assuming that the electronic wave packet is initially unexcited and already in the conduction band, that is a very classical approximations. And then by just coming with the electric field, you will use the Boltzmann equations, and then you will drive the electronic wave packet back and forth inside the blurring zones. Now this is nothing but the acceleration theorems, and by solving this, you will be able to get the electron currents as the integral of your time-dependent occupation functions. And you can get these electric currents, and Fourier transform of these electric currents is nothing but a quantity correspond to the high harmonics that you generate. And now we will ask ourselves, how are we gonna do some spectroscopy, or how do we learn anything about the electronic property using this light? Well, the question is also rather simple. If you are able to make some light out from a given oscillation, so if we decompose, Fourier, using Fourier transform, we decompose the band, conduction band into the series of spatial harmonics, which is nothing but just Fourier analysis. And then you know that if you shine an electronic wave, you shine a light onto this electronic wave packet, onto the sets of this spatial harmonics, each of them will generate its own light. And having each of this own light, they will combine coherently to make the output that you see. So now by decomposing the output, we would be able to reconstruct back what is a set of this spatial harmonics that we are talking about. And by looking at this set, we were able to correlate them to ab initio calculations. And that makes the first experimental demonstrations of spectroscopic in studies of materials, electronic properties using strong light solid interactions. Now we can also show you in detail that our model works so well for different spatial harmonics. You know, this is just a small but rather nice thing that our model works relatively well. And then we will also show that by using this light field synthesizer, by changing the light field on demand, you know that now with this piano of light, we can really change light on demand, and then shooting on the material and detect the response, right? Then we can directly compare, you know, not many groups, have the courage to directly compare theory and experiments. And you can see here that if we compare theory and experiments, there is quite some degree of agreements for different laser pulses. So we really use our laser pulse as the input to the simulations, and then we are able roughly to reproduce experiments and theory. And now people would ask, okay, but maybe that's not enough. We want quantum mechanical simulation, not semi-classical simulation. Of course, we can also do quantum mechanical simulations, but it is rather involved. And the only conclusion we reach is that most of the main features are captured, but it will be very hard to extract understanding, because quantum mechanics simulations are many times similar like a black box. As a side note, we also compare the flux, because if you say that we generate high harmonic from solids, and how does it compare to gas? And we tell you that high harmonic from solid actually makes way more flux compared to gas at the same number of specimen and electric density, electric field density. And we also extend the cutoff energy to 40 eV. And I think that's marks the advance. That's what we think. We think it may not be true, but we think that that may mark an advance of, faster and faster electronic signals processing. But of course, it has a long way to go from our basics demonstration. Now we ask ourselves, okay, what else can we also do? What else can we learn? And we show you that by shooting the laser, now in this case, we don't use very short laser anymore. We use 30 femtosecond laser pulse. Actually, not because we use this, but just because my postdoc group can only do this. So we have this, and we shoot it on given materials with different crystallinity, and we see different response. And as a key question is, what does it mean different response spectrally? It actually means it has something to do with symmetry. So if the crystal is, if the sample is crystalline or not crystalline, there is something to do with symmetry. So that's what people already know. And now, but our experiments show that the response of light-matter interaction has to do with symmetry. And that's exactly where we focus on. Now we set out to do complete polarimetry. So we try to measure the spectrum of the polarizations at different light-matter configurations. And by doing that, we were able to map out quite well the different light-matter response at different polarizations and different incident light configurations. Now, in short, what we do is that we can classify or assign a given response to a given polarizations and geometry of the incident of the material and the incident light. Now, by doing that, we were able to assign what we measured to what is called Berry curvature, which is something to do with the topology or symmetry of the materials. So the detail of this, I will not discuss very detailed here, but the only conclusion we can tell you is that by decomposing what we understood as a Berry curvature, by decomposing also using Fourier analysis and fitting them to the experimental results, we were able to reconstruct the Berry curvature under a given assumption of mathematical models. And with that, we will also compare our experimental measured values, which is this density line, to the ab initio calculation using density DFT calculations. So this is also, both of them are state-of-the-art results, and we get quite some interest, and also I think people are quite excited to have a to see that we were able to connect them. But of course, it is a very first step, and we think that there is quite a big potential going forward along these directions. And as a last part of the talk, we're gonna talk about high order harmonic generations and spectroscopy now in liquids. So you have seen we demonstrate high harmonic generation and spectroscopy in gas, in solid, and now we're gonna talk about liquid. So the question is, why liquids? For people who do high harmonic generations, it is known that it's quite nice to do it in gas, but there is an intrinsic limitation in gas. It's that the gas has very low density, and therefore the flux is not that high. Now with solid, you have a lot of density, right? But then you will come in with another problem that you roughly don't have in gas, which is you have sample damage. Because when you shoot the laser pulse, very intense laser pulse on a solid materials, you likely would burn it, right? Then people would ask, okay, then what about liquids? Well, liquid has the best of both worlds, because the liquid has high density, and because whenever you have a liquid flow, you have a continuous renewal of sample at which it interacts with the laser pulse. So that sounds like the perfect scenario. Well, it turns out that it's not really that perfect, but of course, this is a very first study, so there is a lot of rooms to improve. And previously, of course, there was people attempting to do, but the best people can do was, in the visible domain. And people also do it with extremely high energy and energetic laser pulses, which is called high harmonic from surface plasma and coherent wave emissions. And this has been demonstrated in the past, but not really from the bulk of liquids. So this is in the visible domain, and it is from the surface plasma, not really from the bulk of liquids. And what we're now going to do here is that we demonstrate ourselves, our technology, where by colliding two liquid streams in completely symmetric fashions, we were able to make a very flat Z of liquid. And it is nothing but just the dynamics of the liquid flows, that if you have the completely symmetric liquid flows, so at the collision center, the momentum conservation will make sure that there is no beam on the left or on the right anymore, and then all of them will confine it into the flat Z at the center. And that's exactly what you see here, on one side and on 90-degree sides. You will look at this, you see that there is a different, almost flat Z of liquids that have been generated. And interestingly, it has only like micrometer thickness, and that is really good, or closely resemble our nanometer thin samples. And in the experiment, what we're gonna do is very similar to what we did before, except that we change the target from the solid nanometer thin solid, we change to the flat Z of liquid. And here we're gonna show you the microscopic picture where you can see easily the interaction spot, the laser here, and the plums generated from roughly third harmonics of the laser interactions. And here I even have the videos that I record using the microscope, putting in vacuum chamber. And because it is very small, you can see this diameter here, it is very small, but we successfully do that. So what we do here is that we keep the laser fixed, and then we move the Z up. And what you're gonna see is that the laser interaction spot scan through the Z positions. The laser interaction scan through the Z position, and then if we detect somewhere here, if we detect the high harmonics, we would be able to see harmonics out. And this is how we can detect high order harmonic generation from the liquid phase. And from the gas phase, we know so well that it has been done before. And this is just how we do it in the gas phase to compare and show people that actually we really make high harmonic generation from liquids, but not from the gas. Because people would ask very simple question, hey Trung, you know, if you have the liquid target in the chamber, in the vacuum chambers, you always have vapor pressure, you always have gas molecules surrounding it. So why you are talking about you generating high harmonic from the bulk of liquid, but not from the gas surrounding? And that is exactly how we're explaining to you that due to the refraction of this wedge light liquid target, the different harmonics from gas and harmonic from liquid would go out at different lateral angle. And by having this lateral angle, similar like what you would detect in the camera, you will have different lines of harmonics on the camera. And it is nothing but the raw MCP picture, so multi-channel plates picture, where we detect simultaneously high order harmonic generation in gas and high order harmonic generation in liquids, as you can see. And then we can also show you the video where by moving this liquid jet up and down, this is how we're gonna see that in the beginning you have high harmonic from liquids, and then afterward you don't have liquids anymore, but then you have gas. And this is how they move because you change the wedge angle. So we also do very similar under study as we did before, like we change the intensity of the laser field, and then we measure the electronic response. And we see that, okay, it's also different from gas, and it's quite similar to solid. And because it is similar to solid, we also check, okay, how about the coherencies? And we show you here that it is as coherent as high harmonic from gas. And this is important because the moment you talk about basic science, you need light to be coherent. Incoherent light is very hard to be used for any spectroscopic study. We also generate high order harmonics from liquids and different materials like water and alcohols. You can see we measure the flux and we show that the flux is very similar to gas source, very optimized gas source. So it turns out that high harmonic from liquids might be quite a promising source for generating X-rays. That was a hope. It has not been demonstrated yet, but we hope so. It will be demonstrated soon. And to simulate this, we also simulate the, we try to mimic liquids using the multi-band structure. And we also use a standard semiconductor block equation. We can discuss a bit about later if anybody is interested. But the whole idea is that by using the semiconductor block equation, we might be able to reproduce what we generated. And then from that, we would be able to extract some information. Because our model reproduces the results, we have the right to extract some parameter out. And that can be nothing but the probe of the spatial extension of the whole wave functions. So it has been shown in gas, and now we've shown in solid that the moment you remove the electronic wave packet out and recolliding back, the electronic wave packet keep on expanding and expanding in space. And when it's recolliding back, it has a different expansions compared to before. And by doing this elliptic scan, we were able to map how big is the spatial wave functions. And that is another possible application that we can extract out from such a measurements. And this is nothing but the probing of the spatial extension of the whole wave functions. And recently we also have some further developments, but I would say this is, we will not focus on this now. And I would like to acknowledge all the funding agencies and my group here. We have, our postdoc and PhD students and my former groups and all the funding agencies. And also a small information I want to advertise, if you don't mind, is that we have PhD position opens, and the standard PhD in our group or in Hong Kong would likely get this amount of stipend. But if somebody's having excellent performance, we can apply for the Presidential Fellowship, and you see that the compensation for the Presidential PhD Fellowship is actually quite interesting. And last but not least, I also founded my own companies selling device characterizing femtosecond laser pulse, and this is quite versatile device. And if anybody interested, so please welcome to contact. And thank you very much for your time, and I'm looking forward for any question you have.
So thank you, Trung, for the excellent talks. So very nice illustration as usual. Let's say that if you make a piano blind, so you should be the pianist, and then you play music to discover light matter interaction regimes.
I'm gonna mute.
So maybe now the paper is open for questions.
Yes, please. So we can start, English, Vietnamese, however you like. Yes.
Dạ, anh Tuấn, mời anh Tuấn chị.
Xin chào Trung. Talk rất là hay, rất là good. So I have question about the first question about the laser, the femtosecond laser you use for generate attosecond laser, right? So what is the requirement for that laser? For example, the pulse energy or the pulse duration? What the requirement to get the attosecond from femtosecond laser?
Yes. So yeah, thank you. It's a very nice foundation question. So in order to be able to make attosecond pulses, we need to have some foundation laser pulses, which is nothing but femtosecond. So if you give me a picosecond laser pulses, you will make my job very hard. So we have to start with femtosecond laser pulse first.
Yes.
And the requirement would be that the laser pulse has to be quite intense. What does it mean intense? Intense is as the order of, I would say, millijoule. So let's give you a simple scale, what we are talking about. So the standard laser, if you are not talking, is a standard oscillator that you're gonna buy from the market. You're gonna get if you're talking about picosecond or femtosecond oscillator, you're gonna get something at the order of nanojoule per pulse.
Mm-hmm.
But what we are talking about is we need, in order to start, we need to start from millijoule, so 10 to the 6.
So you need an amplifier.
Yes, so we need to start at about maybe 5 times more energetic than what you could buy with the standard oscillator.
Mm-hmm. Mm-hmm.
5 orders of magnitudes more energetic than what you would have with standard things. So in other words, it's about funding. So yeah, so let's be very frank, right? We're all scientists. So in order to push for very state of the art, you need good funding.
Actually, the amplifier it's not expensive nowadays. You can buy it with like 200,000, right? Dollar, 200,000 pay, for example. You can buy it. And,
that's right, but that is a bare minimum.
Yeah, that's minimum. Just start with millijoule, I think. So when you work with attosecond laser, and the field is very strong and it's short duration, right? So yes. Do you observe something called the plasma wave field or the relativist plasma?
Yes,
right?
Yes.
So because it's
we do,
you also observe.
Actually, that regimes, we can make that regime is slightly, maybe I would say 5 times, maybe to 1 order of magnitude higher than what we usually work with. So if we try a little bit hard, we can make that regime. We can arrive to that regime, but we're not interested in that regimes for the reason that at the moment, if you use very strong laser pulse, you can rip the atoms apart, right? But
yes, so from plasma,
ripping them apart to some extent is less interesting than driving them to the moment they are about to explode, but not exploding yet. Because if they're exploding, you see free electrons, you see, classical trajectory. And that makes the things a bit less interesting for a given group of scientists, where they try to drive to the moment they're about to explode. And then there is many things going on. But when they explode, when they make free plasmas and so on, then it's classical Newtonian mechanics.
Okay, I see. So in order to control that one, normally people control the intensity, right? So the light intensity.
And phase.
Okay. Oh, phase also.
That's right.
So if you work in that case, for example, I think about from pulse to pulse, you need to have some kind of CEP. It means that carrier wave phase stabilization.
Do
you need that one?
That's right. Absolutely.
Okay.
Absolutely. Okay. So that is a very delicate question. So I'm quite impressed that you know this, because this is the fundamental concept behind the I think Nobel Prize in Physics 2005. How people making femtosecond comb, and
laser comb, right?
by controlling the CEP and by fixing the CEP at the given positions in frequency domain, they are able to make frequency comb, or a comb of laser that is super fixed in frequency domain. And that gives them the Nobel Prize, because that gives the precision to determine time 3 orders of magnitudes better than atomic clocks.
Okay.
So in our community, we actually have to do the same, but we're not gonna do it in frequency domain, but we just do it in time domain, which is almost equivalent, right? But we just do it in time domain. And because doing it in time domain, when we lock the CEP, so we know precisely the electric field is moving like this, and it's not oscillating back and forth from pulse to pulse. No, it's really oscillating fixed. And then because it's oscillating with a fixed shape from pulse to pulse, then we know for sure that whatever later burst that we generate in the first pulse is identical to the burst that we're gonna generate in the second pulse, and so on and so on. And that's how we have attosecond resolutions. Without that, it's almost impossible to get the time resolution.
So that's a requirement, right? So CEP is a requirement for you to get it. Okay, got it. Thank you. Maybe it's a last question, and the time for other people.
Please, yes.
So, yes, I saw that you present a lot of the spectrums, a high energy spectrum, right? In the electron volt, few electron volt or more. Do you also doing a time resolve in the attosecond spectroscopy?
Yeah. So, for example, we can.
So how do you control it? Normally, people do pump probe, right? They do the delay state, right? In your case, what do you change? What do you measure the time?
Yeah, we will show you. Almost there. Almost there. Yes. Yeah. Let's do this one. This is a bit easier. Yeah. So this is exactly what we do. Let me do again. So when we make the XUV, the XUV is a high harmonic generations. And then outside of that, it is still an IR. So the driving pulse that is much lower in energy, but much longer in wavelength. And then the XUV is reflected only at the core of the mirror. We actually two mirrors here. It's not one. This is one mirror and this is another mirror.
Okay.
And then this mirror is sitting on a piezo. So then by
Okay, so
moving
you
this,
control the delay by piezo. It's very small movement. Okay, that is
right. Yes,
very hard.
that's how we do this. And this is, you can see it is the outer mirror which is fixed in space, and the inner mirror that is on the precision nanometer closed loop piezo stage. And with this closed loop piezo stage, we can do the time delay, time resolve, right? And you can see the time femtoseconds over here, and you see that each time step we are doing is attoseconds. So our time step is attoseconds. And this is how
that's
we
great.
do this.
Yeah, thank you.
Thank you. Yes.
Yes, so now it's a question for Đức Anh.
Yes, thank you, Tran Trung, for very wonderful books and wonderful talk.
Thank you. Yes.
To be honest, I'm not an optics guy, so I couldn't follow the talk very well. But I'm very curious about the part that you say you measure the Berry phase in the solid using the attosecond. Yeah, could you explain that a little bit more? How can you measure the Berry phase of the solid using the method?
Sure. So let me try to make a very simple pictures. Maybe this. Okay, it's almost here. So now, let me try to make it also intuitively, because if we bring equation here, it will be very long, right? Now, you know that Berry curvature is nothing but a manifestation of the solution of the Schrodinger equations for a crystal with a broken symmetry. For a crystal with perfect inversion symmetry, your Berry curvature, if you are about to calculate it, it should be 0. If you calculate it for a crystal with broken symmetry, the solution from the Schrodinger equation in solid automatically result in non-zero Berry curvature, right? Now, the interesting thing is that because of this, it means that the response of the medium for a given orientation is different, because your symmetry is orientation dependent. So what we're doing, we measure the response at a given orientation. We get this one. You see the mouse? We measure the harmonic response at a given orientations. And then we measure the response at different orientations. And then we see that, oh, the harmonic response are different. Now, the next step is, how do we assign different harmonic response to different orientations? That's where we need a semi-classical model where we have the cross products of the electric field and the Berry curvature. And having the product of the cross product of the electric field and the Berry curvature, now what we're gonna do, we assume that the spectral response is a cross product. And then now, if you only know the outcome, but you only know ET, you would not be able to solve the Berry curvature, for the reason that Berry curvature is a vectorial quantity. So you need more information. And for our technique, it's actually simple. How do we get that? You have a set, what we want to do is we want to make a series of linear equations, but we have only one electric field. What we can do, the answer is very simple. As an experimentalist, we change the electric field strength. So one electric field gives us one linear equations. We change the electric field strength, we have a set of linear equations. And assuming that the Berry curvature is the same, then by having a set of linear equations, we can solve the vectorial Berry curvature. Is this somehow?
Yeah. I could got it in some sense, but I'm related it to the case of like weak topological insulator in the sense that you look at one direction, and then you see different body curvatures, and on the other edge is giving you a different body curvature. So maybe you can use this kind of measurement to probe that topological phase of one material, but from different direction and different symmetry. I think that might be very interesting to get.
Thank you. It's partially done already by a group, by a few groups. Yeah, this is actually partially done. So it's not like completely done, because the theory for topological materials interaction with strong light matter, with strong light, is not fully resolved. The theory is not fully complete, but the experiment has been partially done by two groups, one in China, one in Stanford.
Okay.
So yeah, if you're interested, of course, we can discuss further on this. I can send you the references, and we can continue our discussion on this. This is very interesting, of course.
Yes.
From my side, actually, after we did this, I also tried with topological material, but maybe due to time or some other constraint, I didn't see the signal, so I do something else, and I give up. I do something else. It is how experimental works. And this other group, maybe they wanted to try more and more and more, so then they succeeded. So that's
okay. One quick question: how can you how large is the spot of your measurement? I mean, can you do scanning on the surface or on the on the surface of the sample? Because in some of my sample, I have the center and the edge channels, and the edge channel have a different symmetry and different body curvature from the channel of the center channel. So it will be very interesting if we can do the scanning, 2D scanning of the surface to see how it changes between regions on the surface.
That's very cool. The experimental limitation is a beam size of the laser beam that is at the order of 50 micron. Now there is another challenge, which is we are doing the experiment in the transmission geometry, which means that if the laser beam going like this, we have to detect it over here. But if you're going to put it on the edge of the sample, it might be that the output is not going in this same direction anymore, which means that if we don't see any signal, it may not be because the signal is not there. It just may be that the signal is not falling on our detector. So that is just experimental challenge. We could consider maybe some scheme to overcome this. But yeah, so far that's what I think. Thank you.
Yeah. Thank you. Very nice work. Thank you very much.
Thank you.
So good. You have some questions?
Yeah. Okay, maybe we should mute someone is talking. Okay, thank you very much, Tran Trung. It's a wonderful talk, I have to say, because this topic I think is very difficult, but the way you talk about that is very easy for people to follow and understand that. So it's
thank you.
Yeah.
Thank you.
I have a question. Normally, when people work with the attosecond laser, it seems that it's a very fundamental research, right?
It is.
Yeah, I'm wondering about the application for that study. So do you have any comment?
Frankly speaking, there is very limited application of this. That is also the reason why attosecond science community is mainly based in Europe, because there's where they can have some funding reserve for moonshot experiments, where it may not have anything to do with reality. Actually, in the US, the situation is quite different, because funding for attoseconds is still very limited so far. So it's not like people don't want to try to push for it, but the funding agency, as far as I understand in US, they not yet at the favor of this, following this direction, because there's no immediate applications that one can see except for basic science.
What about
there are of course some application I can say, but from my personal opinions, the amount of applications, I mean really industry application, is very, very limited.
Okay, so let's talk a little bit about your startup. When did you start that, and how far it's go? How many products you have? I'm really curious about that.
Thank you. Actually, I didn't. Thank you.
And what's your research direction now? You keep the same or you move different direction?
Yeah.
So, yeah, this is a good question. Thank you. Is a screen sharing still on?
Yeah, no, but not in presenting mode.
Yeah, sure. I intentionally did that so that I can go back faster here. So, yeah, so here let me. So this is my my startup. So actually, this is nothing but the work that I have done in my PhD and postdoc, and I have a feeling like, okay, you can see it now, right?
Yeah.
I have the feeling that it may be useful for other universities and institutes. So not yet at the level of consumer, but what we do is that we mix a temporal characterization device, which is a device that can measure the pulse duration of femtosecond laser pulse. But usually, as you know, maybe Anh Tuấn knows also quite well that if you want to measure anything in femtosecond, it is very specific things. And if it is very specific, what does it mean? It means that if it can measure, let's say 30 femtosecond, and you plug in, 5 femtosecond, it cannot measure it. Something like this. If it can measure at 800 nanometer and you plug in 600 nanometer laser pulse, I mean the center wavelength at 600 nanometer, it cannot measure it. So then,
what pulse duration you can measure to
that's the key point of my device. Thank you. So that's the key point of my device, because if I show you the device, so this is a photo, right? And the key performance of our device is quite a bit slow. Is that it has almost no limit. What does it mean? Cool. That the pulse durations, you can plug in 5 femtoseconds or you can plug in 300 femtoseconds, it works. No need to change anything in size. Center wavelength, there's also no limit, because if you have a spectrometer, for example, so why I have the star here is because the limit is defined by the spectrometer that we use. Of course, it is a spectrometer. I don't make them myself. I mean, I just buy from a commercial products company. And because it is commercial products, there is a limit for the spectrometer. So our device limit is not actually our device limit, but the limit of the components. And so, for example, if we have now, I mean, what we are offering is a spectrometer, I mean, multiple options. So if you are looking at any spectrometer, if you buy this option, if you buy this model S, for example, and we will use the spectrometer covering from 225 to 1000 nanometer, and that's it, that's the limit. What does it mean? It means that if you can, as I wrote down here, you have a 5 femtoseconds at center wavelength of 500 nanometer, it works. If you have 100 femtoseconds at center wavelength of 266 nanometer, it works. It can measure it. If you have 200 femtoseconds and at 800 nanometer center wavelength, it works.
Beautiful. That's great.
Thank
yeah.
But
how much it costs? How much it costs?
So thank you. So this is certainly quite a challenging question, I have to say, because it is recorded. So I have to be official, right? Okay. And I can tell you, for all the collaborations that we have, I can give you a good discount. But the offer price for this is, so for this model, it starts from 22,000 US.
Okay, 22.
This one starts from 22.
In markets or is still in Asia?
Yeah, not much.
Do you have
I sell it worldwide, but at the moment I don't have yet a confirmed order from the US. We're working on, but We don't have yet a confirmed order. And all the other model, if you have, laser pulse that are in the infrared regions, it is way more expensive for the reason that the detector in the infrared range is way more expensive, right? So this Z1 and Z2 models, they start from 40 to 50,000 US.
Okay.
But for our pricing, as far as I understand, is way more competitive compared to all other companies for the reason that we are startup. So if we sell the same,
I knew the
sorry,
company Swarm Optic. Did you know that Swarm Optic?
Of course I know, because it is how I learned from.
Yes. Oh, okay. They also sell kind of course they have different model, different things also, right?
I know.
Swarm Optic and Frog, it is somehow is similar, right? But the other companies, they sell it, I think it amplitude, they sell it something, they use cross polarization generation, right? The different techniques and there are Swarm and also
that technology is very primitive to what we have. That's what I can say. The information we have is way more than what they have.
Yes, and look like price very competitive. What I can say. If you don't mind, what technique do you use for that one? Oh,
Frog.
You still use the Frog?
Yes, but we have a kind of optimized frogs so that it works quite well. That's the idea. And you know that, I mean, if you look at this thing, right? I mean, it is my hand. Actually, this is my hand. And if you look at the size and the dimension, we kind of optimize. And I have to say that compared to many commercial products of pulse characterization that I have seen, our device is very competitive in so many aspects. If you're interested, please get in touch. I can give you a...
Yes, I contact you as well, Chung. It's very interesting.
The discount.
Yes.
Specific offer.
So for old friend, you should make a very good discount.
And Chung, I think you should have a discount for all the GSC network member.
Absolutely. Please get in touch with me. I will give you each of you individual discount.
Wow, awesome. Thank you. So for the Frog, right, it very much depends on the alignment. If you align the laser not correctly, you can get different results.
So
how about your equipment?
So if you work with commercial product, you know that for all the commercial products, most of them have two irises. And your job as a user is always to align the beam through these two irises. And once you align
inside or outside?
That's right.
Inside or outside?
Inside. So,
inside, so it should be the fixed, right?
Yeah, so it's fixed. So then you just have to make sure that you send your laser beam through these two irises, not completely off. Then roughly you get the signal. Yes.
Okay, thank you.
That's the idea. Thank you.
And Chung, this is the spectrometer for femtosecond laser. So you can measure the width of the pulse and also the wavelength, right?
Yes. So, any laser should have to have a center wavelength.
Yeah.
And the bandwidth, spectral bandwidth, any lasers.
Yeah.
And the only limit of our device is that center wavelength and bandwidth. So if you are running a laser, you must have a spectrometer, I would say. Yeah. Because if you don't have a spectrometer, you don't really know what you have. At least the spectrometer is the first step to characterize. And then for our case, you don't even need to buy the spectrometer. You just need to buy our Frog, because our Frog will give you the spectrometer inside.
But it's only for femtosecond laser, or is it work for other laser as well?
Our device is designed to work for sub 300 femtoseconds. If you want to characterize longer pulse or supposedly longer pulse, it may work, but not so well. And that's, I cannot guarantee. Yeah. It may work, but it's not so well. So if you have like picosecond pulse, well, we can think about, I mean, if you want, we can make a custom order for that. But Yeah, we unfortunately we don't have picosecond pulse to test as a quality
if you
control for
want
you.
picosecond, you can buy much cheaper instead of go to this device. Measure shorter pulse is more difficult than long pulse, right?
Way more.
I think it can be very interesting for people having both picosecond laser and femtosecond laser. It can be some kind of like polyvalent toolbox, so they can plug in to measure every laser they have in the lab. So it's possible to do some custom-made kind of box.
It is possible, but it is, yeah.
And this is how many products you have? Only one or?
At the moment we only have one offering, yes. So
Yeah.
three models. If you are interested, we.
And how many devices you already sell?
This is a sensitive question. I have to say that yeah, we are working on orders, and there are orders coming, and but we cannot say, you know, the specific.
Really,
details.
I think if you say that, then people say, oh, you say a lot, then they trust in your device, I think.
No, I have to be very very honest. We have not sold a lot. Not for the reason that it is not good. I don't believe it at all. If I believe that, I would not make this company. It is not for the purpose of making benefit, because at the moment it is really for the purpose of you know, supporting each others. You know that for the device with such a performance, other company will sell it really, really high. But I don't want to make a profit for now. I want to try to support other people doing the same community, the same business. And then once I have, you know, a good customer base, and then I can expand the product offerings, then I can consider making profit out of that.
Yeah, it's wonderful. You know that Anne Rie, my mentor, she also have a company. You know that one? And
I don't know. Is this Fair Photonics?
yes, Fair ultrafast photonics.
Okay, yeah, that I know. Yes.
Yeah.
Who is that?
Uh,
Who is that? And Trung? She is
yeah,
a leader in
Fair
the
Photonics. Fair Photonics is founded by her postdoc employee, and the guy, his name is Miguel Miranda, and he made the D-scan, what is called dispersion scan. And so what happened is that you shoot the laser pulse, the short laser pulse on the material, and because any material has a wavelength dependent refractive index. So by shooting a laser pulse on a given whatever material, you're gonna disperse it or change the phase afterward. And shooting it after changing the phase shooting that one on the second harmonic, you would be able to reconstruct back the pulse duration. So that is the very nice idea. It works so well because it is so fast and very cheap to implement. And the idea was demonstrated by Miguel Miranda, I think somewhere around 2010, you know, while he was doing PhD in Portugal in combinations with Anne Huile at that time. And then when he did the postdoc in Anne Huile's group, and then they founded the company Sphere Photonics, I think somewhere around 2012, and they start selling this device actually. And the good thing of this device is that it's very fast, it's relatively cheap, it's easy to use, but the not so good thing is that the universality is not as good as our Prof. So if you say that you want to measure 5 femtoseconds, they have to say, okay, but then you cannot measure anything else, okay? You have to say that you only measure this. So in other words, when you have a laser, you buy the laser, and then you tell them that you're gonna buy the characterization device from them for this laser, then they're gonna be able to do it for you. But they cannot do what we are offering. For example, you buy one of our device, and then you bring it to your lab, to Anne Huile's lab, to Tran Chung's lab, it works. But that you cannot do with other Sphere Photonics products. That you cannot do.
But when I look at the website, I see that they have many products now.
Yeah, of course they're offering. So the guy, he told me that I think he somehow, I'm not 100% sure, but probably he quit his academic position to focus on his group, I remember. But I don't know so well anymore. Yes.
Yeah. And Tung asked about Anne Lie. Anne Lie, I think she is the leader in the attosecond. Is this right, Anne Trung?
Anne Hui Lê.
Yeah. And
You
she,
know, the paper that I show you here.
yeah,
I think this one. I think this one. Anne Hui Lê is a co-author.
She I think last
So she is, you know, one of the founders.
Yeah, last year she received
The Wolf Prize. Yeah, yeah, it's a very prestigious prize from Israel for science, and it's considered close to Nobel Prize. Yes, not yet, but yes. So Anne Hui Lê is of course very respected scientist.
She French Swedish scientist, and she working in Lund now nearby me. So she mentor me now in my
Yes, she has been there for years, like for decades.
Yeah.
Yes, so she's very nice. She's excellent scientist.
Yeah.
So, is any other questions for
Thank you.
I have two naive questions. So,
yeah, please.
How do you calculate the band structure for liquids? What is you know, when you
Okay, so very good question. So okay, maybe I can elaborate a little bit. First of all, I cannot calculate a precise band structure for liquids. That's just a declaration. And more precisely, the terminology band structure doesn't exist for liquid. For the reason that when you talk about band structure, the moment you spell out band structure, you automatically assume that you have periodicity. And that doesn't exist in liquid, right? So now what people can do is that let's assume that we can mimic something like a band structure of liquid. First of all, we do that, right? Then there are so many ways you can do approximations, because different way you approach the problem with different approximations, you will come up with different results. So what we did specifically, we try also different techniques. First of all, I try to do real band structure calculations where I take the atomic structure of ice with 9 or 11 structure of ice, and then I mix them. Or you can mix them, using multiple techniques. But after you mix them, you get a specific arrangement. Then I plug this supercell into the DFT calculations. I get something out, right? But that also depends so much on all the parameter you put in your DFT and all your exchange correlations, all of these settings. Then in short, that will give me almost random results that is not really relevant to any publication so far. So then we give up on that. The next thing we try to do is we don't do calculations, but we just take the X-ray measurements and just take the X-ray measurements, experimental results, right? From X-rays measurement, absorptions and absorption and emission spectroscopy. We take that X-rays measurements, then we can extract more or less the density of state of the conductions and valence bands. And then by having that, so this thing is nothing but the measurement. The graph I show you on the left is a measurement, X-ray measurement. I don't remember whether absorption or emission spectroscopy, but from this we get this density of state. And then from the density of state, we try to mimic it with a 5 bands models. Now, of course, this mimicking using 5-band model is also very coarse. You can tell me, yes. And I have to admit, yes. And then after that, we recognize that we don't have the dipole transition dipole matrix elements because we just don't have that. So then what we decide to do, we just put in, normalize transition dipole matrix elements. We perform the semiconductor block equation calculations. Then we recognize that the result out from this 5-bands model is very similar to the result just from the conduction and first valence band. First valence band, first conduction band, it just seems very similar. So after doing this, then we say that, okay, if it is similar, then from now on, we only use 2 bands. So this is how our reasoning or like flow. We start from the experimental measure X-range measurements. We come on with we arrive with the density of state, and then we mimic with 5-bands model. We recognize the same as 2-band or almost the same as 2-band. Then we use 2-band models, and from the 2-bands model, we try to plug in the incident electric field, and then we do a series of calculations with a variable parameter like electric field intensity and so on. And for different density of state of water and ethanol, and then we have to compare it or benchmark it with the experimental results. And this is where the ETS early cluster is very useful, because I have to send like 1,000 core for like 1,000 CPU for like maybe a few weeks, and then after that I get these results, and this is quite good. And this is what we think it is good, but of course we don't know for sure it is long lasting. That's we don't know, but at least so far it is the best that we try, and yeah, it's more or less okay. So sorry for the long answer, but I hope
it's very clear. It's very clear. Yes. So my other question is also relating to the very curvature that I already asked. Maybe we already answered, but I want to know precisely that you did try some kind of real topological materials like bismuth, selenite, things like that, and there's no signal, right?
No. I did not try this type of materials. I did not. Yeah, because there was too many things to do. So there's some things I can do. So yes, I cannot do a lot of things.
Yes, and also questions already discussed by Kung about the applications. Because nowadays people mention XUV or NUV for free mask optical lithography, because when you reduce the wavelength, then the diffraction limit become very small. So you can make very small pitch of lithography compared to standard UV lithography. So how do the UV, the XUV generation from your case compared to the one people try to use in XUV lithography? Is it possible to have applications in this field?
Yeah. So first of all, very nice question, very relevant question, and I have to tell you it was probably the biggest promise of this community for an application in industry. But so far, to the best of my knowledge, it doesn't work. The reason is very simple. The efficiency of the high harmonic generation process is at the order of 10⁻⁵ to 10⁻⁶. Now, if you compare that to the state-of-the-art incoherent X-ray generations in lithography machine right now at the order of 10%, we are still, 4 orders of magnitude less. So what I know is that actually I was lucky to have a chance to actually visit ASML factory and company headquarters. Then I know that they were able to make incoherent X-rays by shooting extremely strong laser on thin droplets and collecting using 0.5 meter spherical mirror. And by doing that, they were able to generate about 10 watts of 13 nanometer light. And 10 watts of 30 nanometer light, I tell you, is just beyond what anybody can do, any feasible things that we can do in academics. So in industry, they really lead this incoherent X-rays, generation, you know, by decades compared to the lab that you can do by any other techniques.
But
10 watts of
yes, I understand that for lithography you don't need a coherent light, but still you need a collimated beam, so to focus in the small spot. And
That's right.
And the fact that you have coherent light make it a collimated beam for free. But if they have like very high power, but the beam is very divergent,
that's what I said. That what they did. So I still remember what they did is that they put the droplets of tin dropping, right? So every time it's a droplet, like I don't remember the size, but it's a droplets, and it fall down, and then they have like kilowatts laser shooting on it, and then they know that it is incoherent X-ray radiation, so it's in 4 pi. So 4 pi steradian. So what they're gonna do? They make half a mirror, spherical mirror. So it's like very well designed.
Okay, so they put it in the focal of the mirror.
Half of, yes, the interaction point is half, I mean, at the center of that spherical thing. And it is huge. I mean, I remember it like this. And then they shoot in by kilowatts later, and then they get out 10 watts of X-rays and 10 watts of X-rays. This is how they're gonna sell their products. So each of their lithography machines start from 10 mil to 100 mil, right? And it runs 24/7, 365. This is how they pump out money, right? So this is different scale. And I know that ASML actually founded the ASML Research Center together with University of Amsterdam to focus on finding the new source of X-rays to support lithography processes. And actually my former colleagues got a position there, but I didn't apply because honestly, I really think that this direction at the moment, without any breakthrough, is a dead end. High harmonic is not applicable for this. It can do something else, but it cannot compete with incoherent X-ray generation so far. Just 4 orders of magnitude is just too much.
I can ask also a question on your current research direction now. I think.
Yeah. Sorry, I missed it. Yes. So current research directions, I also I wrote it in the website. We have 2 main research directions. One is in basic science. One is a little bit more engineered. So basic science is where we try to generate high harmonic spectra and try to do time resolved spectroscopy and try to study electronic dynamics at the attosecond time scale. This is the first thing that we try, mainly on the solid materials. On the other hand, we also put some effort on the engineering aspects, which is to generate optimized light source. So we try in this direction, and we do have a few ideas how we might be able to improve the XUV light source. And for this direction, Hai-Sen knows very well because I was discussing with Hai-Sen on the possible proposal on this particular direction, how to roughly engineer the high harmonic generation efficiency on solid. And Hai-Sen is expert on this, and on nano photonics. So I think maybe we can try to join force and do something together. That's what I think. Yes. So we are working on this engineering aspect. The scientific aspect, of course, we still try to do, and also partially related to the question of anh Hảo chứ. It was like because for this interest, it's quite hard to bring our resources back to Vietnam, you know, because of mainly funding and the main research directions of Vietnamese community, which I fully understand. I mean, there is nothing to say. It does, you know, we have different interests and we respect each other interests, and that's it. So if we are not compatible yet, it's okay. We may be compatible later.
Yes.
May I ask you, Andrew? Because I know there is other group work with harmonic generation. So what is the cutting edge of your research now?
That's right. That's a good question. You know, this is also what I have to justify for every PhD or postdoc that we are about to hire. Because then they ask, okay, there's so many groups, and what, you know, what is new from your research? I have to say, not so much, but we are open. We are open, and we have quite a strong focus on optimization overall. And we keep our mind open for open scientific discovery, and we have to keep an engineering mindset to optimize all the processes that we have. And you have seen so far also, due to my experience, that you know, most of our publications so far was they have quite a strong engineering background. You may not see it because you are not in the community, but if you're in the community, you will see that many papers that we publish, 10 years later, there was no competing paper. So so if you are in the community, you see, okay, this idea may not be new, but if you are really well advanced in engineering, you whatever you do is likely new. And you can say, okay, I know the idea, but actually you can say that to almost everything else. Right? When other people publish paper, you say, oh, I also know this idea, but it's important whether you can do it or not. That's very important. So for example, the piano of light, that experiment, the piano of light was actually proposed by Tran Trung Luu, so the Nobel Prize, the Nobel laureates, in 1992. But 20 years later, it was demonstrated by our group. Not because that, you know, this idea is new. No, we say we just learn from Tran Trung Luu that there is, it is possible, but I think, in the visible domain, until now, so 11 years after our publications, until now, there is no competing works in the visible domain.
Yeah, I see. Thank you.
Thank you.
Now, I see India has some questions.
Hello.
Xin chào anh.
Xin chào tất cả mọi người, nhất là Trung, cũng có nói chuyện với Trung thời gian lâu rồi.
Chào giáo sư Điệp.
Hello, Tuấn chưa đi ngủ à?
Hay quá.
Anh
hay quá
chưa có
Anh chào anh Điệp.
Rất là hay nghe bài của Trung. Thực ra là mình cũng làm một optic, nhưng mà có những cái cao hơn, có xa hơn quá rồi, cho nên nhiều khi không biết gì, nghe cũng không hiểu nhiều lắm. Kiến thức của mình chỉ dừng lại ở attosecond laser thôi, cho nên là ato thì nó hơi xa một tí.
Giáo sư khiêm tốn thế này.
Thế cho mình hỏi một tí để hiểu thêm một tí về Asst ấy. Mình cũng có thăm một vài phòng thí nghiệm liên quan đến Asst, nhưng mà khi mà mình làm về nói tiếng Việt được đúng không? Tại vì hình như hết các bạn nói tiếng Anh rồi.
Tiếng Việt thoải mái.
Khi mà mình làm việc ở cái mức độ Asst ấy, thì lúc ấy cái khái niệm về bước sóng với lại cái xung đấy thì thế nào? Tức là cái xung ấy rất là ngắn đúng không? Nó ngắn hơn cả bước sóng. Thế thì trong cái xung đấy mình sẽ hiểu thế nào? Tức là không nói về cường độ, mình nói về trường thì âm dương rồi mọi thứ thế nào, mình sẽ hiểu như nào nhỉ? Cái đoạn đấy mình không hiểu lắm.
Dạ vâng anh ơi, tức là thế này. Để em lấy cái này nhá. Đây, cái này là cái dễ nhất này. Thì anh nhìn thấy screen này đúng không ạ?
Dạ.
Nó vừa chạy mất rồi đấy.
Anh nhìn thấy screen chưa?
Rồi.
Ok, bây giờ nhá, là nếu mà anh có một cái bước sóng này thì nó sẽ tương ứng với một cái pulse như thế này.
Đúng rồi, tức là trong cái ok.
Đúng
Tức
chưa?
là attosecond laser thì mình vẫn hiểu được. Thế nhưng mà đến atto
Đấy.
thì
Thế bây giờ anh cứ
cứ
tưởng tượng là vậy, anh cứ nhìn cái mouse của em để em lấy cái laser pointer.
Nhưng mà thế này anh Điệp ạ, tại vì cái bước sóng này bây giờ là bước sóng ở extreme UV chứ không phải visible nữa, nên bước sóng nó cũng rất là ngắn.
Đấy, tức là khi mà mình làm atto là mình không phải là bước sóng trong vùng visible hoặc này khác nữa đúng không?
Tức là cái quan trọng không phải là cái bước sóng của anh trong vùng nào, mà là cái bandwidth của anh nó có đủ rộng hay không. Cái bandwidth là cái rất quan trọng, bởi vì cái bandwidth
Đúng rồi.
nó sẽ define là làm sao cái mức độ engineer anh có thể làm đối với cái laser pulse đó. Nếu
nhưng mà
mà
cái bandwidth là mình phải
anh rất bé,
đủ lớn sang vùng UV thì nó tức là vùng ultraviolet thì nó với cover được hết đúng không?
Cứ phải cover cả từ IR đến UV thì nó phổ rất rộng thì pulse sẽ ngắn. Thế thế mới phải trộn trạo các bước sóng với nhau để tạo thành là như thế. Thì nếu mà chỉ có một, tức là dùng rất nhiều bước sóng của femtosecond laser để mix lại thành một cái attosecond laser, nếu mà không biết hiểu thế
đúng rồi. Đúng rồi,
Ok.
về mặt bản chất là như thế. Tức là em nói lại này, nếu anh chỉ tưởng
vẫn giống như là nguyên lý tạo ra xung femtosecond laser thôi. Nhưng anh cứ tưởng là nó không phải thế.
Không, giống hệt. Về bản chất là giống hệt. Chỉ có khác một cái là với femtosecond laser thì anh có rất nhiều cycles. Khi mà anh có rất nhiều cycles thì cái mức độ engineering của anh nó sẽ ít hơn. Anh vẫn engineer được nhưng mà nó sẽ khó hơn. Và cái engineer của anh nó không đạt được đến cái mức độ extreme, đến mức là anh có thể tạo được cái pulse như thế này. Thế để tạo được một cái pulse như này thì anh phải cần có rất nhiều bước sóng. Rất nhiều bước sóng từ đây đến đây.
Ok, tức là nó vẫn là nguyên lý của femtosecond laser, vẫn cứ
Đúng
phải
rồi.
là dạng mốt lấc rồi các kiểu thôi đúng không? Okay.
Chính xác, anh phải bắt đầu từ cái đấy.
Ok.
Nên là như anh Tuấn Trịnh nói là về mặt bản chất là em phải có một cái starting rất là tốt, cũng khá là expensive. Nếu không có cái đấy thì không thể làm được.
Tức là vậy là giáo sư Tuấn bảo là nhất thiết phải UV thì không phải, không nhất thiết. Thế anh hiểu là visible mà, nhưng mà nó là phải atto.
Nó là phải broad bandwidth, anh cứ hiểu là phổ rộng như kiểu Hải Sơn nói. Cứ phải phổ rộng, còn nếu phổ không đủ rộng, tức là quan trọng trong cái này em nói là cái phổ của nó phải là đâu rồi đây, cái phổ của em là
đến cùng bước sóng bao nhiêu? Không, cũng là two octave, nhưng mà đến bước sóng khoảng bao nhiêu? Bước sóng ngắn nhất
270
ok
cho đến 1000, mà continuous, mà coherence, intense nữa. Tất cả các condition đấy anh cộng vào một lúc. Phải broad bandwidth này, xong rồi continuous này, xong rồi intense. Thì cái này nó có là thì khi mà anh có đủ các condition như thế thì anh sẽ làm được cái piano apply.
Xin lỗi mọi người nhưng mình lại phải đi sang một cái meeting nữa.
Okay.
Đấy, thì cảm ơn rất nhiều. Để đấy thì có gì chung tí nữa mình mai là chuyện tiếp cho nhá.
Ok Hải Sơn, chiều mai gặp lại nhá, sáng mai gặp lại.
Bye bye Sơn.
Bye. Đấy.
Ok, vậy là cái phương pháp mà tức là nếu mà các cái nhóm bây giờ nó làm cái super continuum này thì tức là nó có một cái liên hệ rất là chặt chẽ với cái attosecond đúng không?
Nếu mà để làm được attosecond thì anh phải có super continuum.
Ok.
Nhưng nếu anh có super continuum anh chưa chắc đã làm được attosecond.
Đúng rồi. Bởi vì cái bọn super continuum hiện nay thì cũng chỉ đến từ picosecond laser, mấy femto, xong rồi nó ra mấy cái xung nano thôi. Okay.
Vì em bảo là anh phải có tất cả các yếu tố hội tụ, nghĩa là anh phải có super continuum này, sau anh phải có là coherence này, sau anh phải có intense nữa, tức là cái pulse energy nó phải đủ lớn. Ví dụ như là các lab mà làm super continuum thì thường người ta super continuum của người ta ở cái mức độ level là nanojoule. Nanojoule. Thế nhưng mà cái pulse này, cái này của lab em là order của nó là 100 microjoule, nghĩa là nó khoảng 4 orders of magnitudes more intense,
Okay.
more
Anh
energetic.
vẫn quay lại cái thắc mắc đầu tiên. Thế ok, thế nguyên lý thì ok, nó giống như nguyên lý của photovoltaic laser rồi, nhưng mà thế thì trong một cái xung bây giờ nó cực ngắn rồi. Tại vì photovoltaic laser thì vẫn kiểu như 10 photovoltaic với lại 100 photovoltaic thì mình vẫn hình dung là ở trong đấy là vẫn tồn tại 1-2 bước sóng, đúng không? Nhưng bây giờ nếu atto thì bây giờ nó không tồn tại hẳn một cái bước sóng nằm trong đấy luôn, trong cái xung đấy.
Trong một cái attosecond pulse thì lúc nào anh nhìn vào nó anh cũng chỉ thấy màu white light.
Tức là mình sẽ không thể có được một cái oscillation ở trong cái pulse này nữa.
Anh có cái này, anh có cái này thôi. Anh có half a cycle, bọn em gọi nó là half a cycle, nghĩa là có một nửa cycle thôi.
Có một nửa cycle.
Như là bình thường anh ví dụ continuous wave thì là infinite cycle đúng không?
Ok, rồi.
Attosecond thì anh sẽ có khoảng ví dụ như là 100 cycles.
Ok.
Đúng không? Thì nếu mà bây giờ anh cứ add thêm wavelength, add thêm wavelength, xong rồi anh mix nó cùng một timeline thì là
đấy cái
anh
có tưởng tượng đấy, tức là có tưởng tượng về bước sóng ánh sáng thì mình cứ hình dung là nó phải có oscillation đúng không? Có dao động, có chuyển động. Bây giờ tự nhiên trong cái
đây bây giờ em giải thích cho anh rất là dễ. Em giải thích cho anh cái này cũng không phải là cái gì chẳng, tức là bởi vì anh chưa familiar nên là nó khó tưởng tượng. Bây giờ em giải thích nhá. Tức là thế này, nếu mà anh look vào cái anh nhìn vào cái phần này của waveform nhá.
Ok.
Cái phần này của waveform không có nghĩa là nó không có một wavelength nào hết, mà có nghĩa là nó có tất các wavelength, nhưng mà the sum ở tất cả các wavelength này là
nó
destructively interfere.
phase nó different, nó trái phase.
Thế thôi. Chứ còn đấy là chuẩn là phải như thế, là anh phải nhìn là thật ra cái femtosecond của anh không phải có nghĩa là out of cái laser pulse đấy thì không có color nào, không đúng, mà vẫn có color, nhưng mà các color đấy nó destructively interfere, nên khi mà anh measure thì là nó bằng 0 hoặc là nó gần 0, nhưng mà về mặt bản chất là nó vẫn có. Nếu anh nhìn vào cái góc nhìn đấy thì sẽ thấy là nó khá là make sense, mà cái đấy thật ra về mặt bản chất nó chỉ là Fourier transform, Fourier analysis.
Ok, thank you very much. Có một cái nữa liên quan đến cái tạo ra cái high harmonic ấy. Có những cái bài gần đây nó kết hợp với lại plasmonic chẳng hạn, thì em so sánh thế nào những cái phương pháp của em với lại cái
em chỉ biết là có 1-2 bài kết hợp với plasmonic thôi. Và theo như em hiểu là cái bài mà Nature Physics mà kết hợp với plasmonic đấy,
cái bài đấy
được sai rất nhiều. Nature Physics, I think, em nhớ hình như là 2011 thì phải. Bài đấy được sai rất nhiều, nhưng mà thật ra là sai là bởi vì nó sai chứ không phải là bởi vì là nó interest.
Đấy à?
Nên là sau khi cái bài đấy được sai rất nhiều, bài đấy cũng được sai rất nhiều, nhưng mà mọi người sai là bởi vì mọi người phát hiện ra cái này là không đúng. Thì có một cái group ở Đức là cái bài plasmonic và high harmonic kết hợp lại với nhau, thì bài đấy là của Kai, South Korea, trường cũ của em. Nhưng mà sau khi họ publish bài đấy trên Nature Physics thì có một cái group ở Đức họ không tin lắm, họ làm lại, xong họ phát hiện ra là thật ra cái này không phải là high harmonic, mà cái này chỉ là resonant emissions của cái atom đấy thôi.
Okay.
Thế là thật ra cái giải thích theo như em hiểu đến giờ thì không phải là mình nói là chắc chắn nó không thể xảy ra, nhưng mà theo như em hiểu là gần như nó không thể xảy ra, bởi vì là hai cái community này deal với cái intensity hoàn toàn khác nhau. Với plasmonic là anh hoàn toàn là linear physics, trong khi đó high harmonic là anh phải go beyond perturbative optics, anh phải go beyond perturbation theory. Vậy hai cái community này là dựa trên hai cái concept hoàn toàn khác nhau về mức độ strong của electric field, nghĩa là cái mức độ lớn mạnh của electric field là hai cái regime hoàn toàn khác nhau. Nên là một cái plasmonic là anh hoàn toàn là phải là linear physics, nên là electric field của anh là phải weak, không được strong lắm. Trong khi đó high harmonic thì anh phải vượt quá cái perturbative response, là cái electric field của anh là phải strong ở một mức độ nhất định rồi. Thì về mặt bản chất theo như em hiểu là hai cái regime nó khác nhau thì anh gần như anh không thể match được với nhau. Tất nhiên có thể sau này mọi người có thể sẽ nghĩ ra được những cái mới, nhưng mà fundamentally theo như em nghĩ là không connect được, không connect community được.
Ok. Đấy, anh
Tức
cũng
là
hay đọc,
để anh có
đọc bài
plasmonic
đấy, xong hay nói chuyện với giảng dạy, cứ hay đưa cái bài đấy vào liên quan đến quang phi tuyến với lại cái sự tăng cường của trường nhờ vào plasmonic, nhưng mà nếu em nói thế thì cũng phải cẩn thận đúng không?
Vâng, thì thật ra thì cái này nó là state of research thì có thể theo như em nói bây giờ là theo như em hiểu thì như thế là chưa hợp lý, nhưng mà 10 năm sau có thể người ta lại bảo là thật ra như này là hợp lý. Thì mình cứ cẩn thận, mình cứ nghĩ là đây là lời Trung nói và đây là lời ví dụ họ nói, còn nó có đúng hay không thì là reader phải tự judge.
Cảm ơn rất nhiều nhé. Ở trong
Dạ,
cái
vâng.
nhóm của anh này có Ngô Gia Long là em của Trung. Ngô Gia Long là làm cùng với thầy Bình đấy, Nguyễn Thế Bình đấy. Bây giờ đang làm nghiên cứu sinh.
Thế ạ?
Ngô Gia Long là biết Trung đấy, biết Trung biết Long.
Thì như em cũng có nghe tên thì phải.
Ngày xưa cái đợt mà em tốt nghiệp đại học em cũng làm với thầy Nguyễn Thế Bình mà.
Thế à? Thế giờ em đang làm đâu?
Chuyên lý tổng hợp K24.
Long đang làm.
Thế giờ em đang làm
nghiên cứu sinh với anh Trung.
Em đang làm PhD với thầy Điệp ạ.
Tiếc quá, không để bảo anh bảo sang Hồng Kông.
Em năm cuối tiến sĩ rồi.
Postdoc nha, Postdoc là Hồng Kông nhá.
Postdoc.
Rồi ngày xưa em
postdoc thì
đợt tốt nghiệp đại học em cũng xin anh mấy cái kinh nghiệm để du học châu Âu, tại vì em thích đi châu Âu.
Đúng rồi.
Vâng. Anh có viết ra một cái nốt rất là hay.
Em thông cảm anh, không nhớ lắm, tại vì anh cũng advise bạn nào nhắn tin anh cũng cố gắng trả lời. Nên là...
Anh Trung cho em hỏi một tí về cái em thấy cái group của anh nhiều người thế nhỉ, 2 postdoc rồi 6 PhD à?
Đúng rồi.
Rồi thế thì funding nó như thế nào, nó phải rất dồi dào thì anh mới có thể mà trả lương như thế chứ, như ở bên em là thôi group như thế là lớn lắm luôn á.
Funding thì thế nào nhỉ, mình cũng cố gắng là như anh em bên US là nửa thời gian chỉ có viết grant. Tỷ lệ approval funding của mình chỉ khoảng 15%. Viết 7 cái thì được một cái.
Thế sinh viên bên Hồng Kông đấy là mình trả tiền hết hay là họ có thể nhận tiền của trường hay là làm TA?
Cái đấy thì tức là sinh viên thì tùy vào cái arrangement của trường, department của em thì họ thống nhất là trước khi em đến là đã có cái rules là thống nhất là cái funding của university mà cho department thì sẽ dành một lượng gần hết để fund PhD.
Tuyệt vời luôn.
Còn tiền mua
vì như thế
sao?
thế nên là nếu mà như vậy thì anh nói đúng. Nếu mà như vậy thì đối với người lớn, người mới đến ý, thì là phải cố gắng rất nhiều để apply external funding để kiếm equipment. Thì em nghĩ là theo như góc nhìn của em thì lab em cũng khá ok, tại vì bây giờ em có 2 laser và cũng một số bạn để làm.
Thế là nhiều quá.
Nó lại ngược bên Mỹ thường là cái external funding nó lại không fund cho equipment, tất nhiên là vẫn có nhưng mà rất là ít. Còn cái equipment thường là trường nó sẽ đầu tư cho mình ngay ban đầu, rồi sau đấy mình
nhưng mà thế là nhiều đấy.
Thế là
nhiều đấy. Em thì em cứ phải đi lượm nhặt thôi, cứ funding cứ bao nhiêu nhỏ cũng viết mà lớn cũng viết, nói chung là
chỉ có Mỹ mới nhiều tiền thế thôi.
Dạ.
Chỉ có Mỹ mới nhiều tiền thế thôi, chứ còn anh em mình châu Âu với châu Á thì
đó,
anh ơi, cái community của em thì châu Âu là nhiều tiền nhất.
Anh Tuấn là còn được cho lúc đầu người ta cho anh là 700.000 đô nha, để xây dựng thiết bị phòng thí nghiệm, đúng không anh? Rồi
khoảng thế, nhưng mà anh cũng phải để một phần để thuê sinh viên, nên là anh không
nhiều vấn đề
đâu.
đúng không?
Em chắc là bên chỗ em là khổ nhất luôn. Em bắt đầu không có thiết bị, không có tiền cho funding và lương người ta chỉ trả cho em 80% lương. Rồi sau khi mà promoted lên thì người ta sẽ trả em 50% lương thôi.
Như thế thì gọi là
mà
cái gì
sống ở
nhỉ?
luôn sướng.
Vươn lên trong cái đấy thì nó mới là tài năng, đúng không? Đấy
Em,
mới là
em cảm thấy bị
như bọn em. Thế nhưng mà như thế là kiếm được funding thì sẽ có thêm được project để làm.
Dạ, nhưng nếu mà funding em xin được funding lớn tầm 400.000 euro nhé. 400.000 euro em chỉ đủ tuyển một PhD thôi. Bởi vì bên này overhead cost là 55%.
Wow.
Lương PhD rất cao. Lương PhD bên này chắc phải hơn lương postdoc ở bên Pháp đấy. Rồi
nói chung là bên châu Âu
là... như thế thì em chỉ đủ tuyển một PhD thôi. Và cái funding lớn tầm đấy là cái tỷ lệ thành công, nghĩa là chỉ được 11% người apply được cái funding đấy thôi.
Cương tuyển được chưa? Tuyển được nghiên cứu sinh chưa?
Dạ em tuyển được rồi anh ạ.
Ok, chúc mừng. Bạn nào may mắn thế?
Có một bạn người Ấn Độ, em mở cái call đó ra thì 40 mấy application thì em chọn được một bạn Ấn Độ.
Thế là
đưa lên mạng thì đông ạ. Giáo sư Tuấn tuyển được chưa?
Em tuyển được một, hiện tại cũng có một nhưng mà em đang muốn tống nó đi tại vì nó lười quá.
Người nào nước nào vậy anh cũng?
Thằng lừa thì thằng Bangladesh, còn một bạn Việt Nam thì bị sao?
Tuyển Việt Nam đi, ưu tiên Việt Nam đi.
Yeah. Hôm trước trong các bạn apply có một bạn người Việt Nam ở trường Đại học Sư phạm Sài Gòn, thì em định gọi bạn đấy cho interview thì bạn ấy lại nhận được job ở bên Na Uy, thế là bạn ấy chọn ở đây luôn trước khi mà em interview.
Tất nhiên là tuyển PhD khó mà.
Yeah. Em nghĩ là cái quan trọng khi mà tuyển PhD là cái bạn nào ngoại trừ background ra thì phải có high motivation đó. Cho nên anh Tuấn mà bị dính một bạn là lười là và việc mà nhận ra được cái high motivation của nó phỏng vấn hơi
đứa mà anh đang có này nó hơi bị low motivation nên là là không ứng từ đó.
Khó nhở anh Tuấn ơi, nhưng mà bên Thụy Sĩ bên Mỹ nó có cho làm mấy tháng thử việc không?
Có, nó khoảng độ, thực ra nó cũng không phải thử việc mà nó có khoảng độ 1 năm 2 năm gì đấy, mình phải qua những cái test, những cái course gì đấy thì mới được chính thức làm PhD chẳng hạn. Đấy, thì nếu mà mình không thích thì mình cho nó fail cái test đó.
thế à? Có việc tuyển được. Ở bên em mà tuyển vào rồi là không có đuổi đi được đâu.
Có. Bên em có 3 tháng luôn giống luật châu Âu là phải có 3 tháng thử việc. 3 month probation.
Có. Đúng rồi, bên Pháp cũng không có đâu, bên Pháp vào là 3 năm là dính đấy.
Không có đâu.
Không có
đuổi hơi khó đấy. Không, bên này ký hợp đồng là làm thôi.
Bên châu Âu nhân đạo hơn.
Nó nói vậy thôi.
Thế nhỉ?
Nhưng mà đuổi
Bên
khó
châu
lắm.
Âu này nếu mà trò không làm là thầy làm thôi, thì thầy cho phải làm 3 năm để cho ra trường đấy.
Thế à? Sao lạ thế nhỉ? Anh Điệp em ngồi em làm
Ngô Gia Long bây giờ có
PhD.
thể không cần làm, cũng ra trường được.
Ngô Gia Long thì làm hộ thầy rồi, không lo rồi, chỉ có lo nghề khác.
Tôi cứ tưởng là thầy cho không làm, thầy làm thì cứ ăn chơi cho thầy làm.
Ngô Gia Long giờ thầy toàn cắp ô đi cắp ô về thôi, có làm gì đâu.
Học trò làm hư thầy quá.
Không tìm được học trò như thế là perfect.
Dạ đúng rồi.
Khó lắm, không dễ đâu.
Em bảo các bạn lớp em là bây giờ các bạn cố gắng làm sao mà đừng nói chuyện với tớ, mà các bạn chỉ cần cứ làm đi, xong rồi 3 tháng gửi tớ một cái manuscript.
Anh thầy hỏi tới em còn là chả làm được.
Tất nhiên là động viên các bạn như thế.
Bên Hồng Kông là đắt đỏ nhỉ? Thế mà cái stipend là lúc nãy em nói là 27.000 à? Có vẻ không cao lắm đúng
Đấy,
không?
anh chị mà có biết bạn nào mà ở Việt Nam good thì giới thiệu cho em. Em cũng muốn tuyển.
Cái tiền đấy có sống được Hồng Kông không? Cái tiền mà 27.000 năm nó có sống được Hồng Kông không?
Anh ơi, chỉ vừa đủ.
Chỉ vừa.
Đâu rồi?
Anh Trung viết vào email trong cái group network của mình có nhiều anh chị ở
quảng cáo số to thế nhưng mà thật ra là chỉ minimum.
Tức là nhà Hồng Kông đắt lắm đúng không? Nhà thấy nghe nói kinh khủng.
52.000 đô, 52.000 đô trên năm mà chỉ đủ sống cả, kinh nhỉ?
không tiết kiệm được mấy đứa bạn nào.
Là president chứ còn bình thường có 27.000 đúng không? 27.600
Đúng rồi,
này.
cái mà em tuyển lab em trả ấy là cái này.
Ok.
Em trả có tên em.
President fellowship
Nếu mà
thì rất là
funding
khó,
của em là cái này thôi. Còn lab em có một bạn được cái đầu tiên.
Anh Trung, còn bên em BD là nuôi được cả gia đình cơ. Dạ thật như thế mà, một BD bên này là nuôi được cả gia đình đấy.
Sống luôn sướng, sống ở đấy sướng mà. Sống sướng nhỉ. Chứ bên này mà bạn nào mà đưa vợ sang là vẫn được nhưng mà sẽ rất chật vật.
Thế nên nhưng mà khổ đó, bên này anh tưởng tượng ví dụ như anh như thế này thì một BD của anh thì anh cần rất là ít tiền, trong khi một BD của em phải xin grant rất là lớn.
Không, thời gian nói nó khó lắm, bởi vì thế này, cái funding mà của department nhá, như bên mình là mỗi department nó sẽ có funding cho từng người đúng không? Thì
em
cái department có, chẳng qua là cái allocation khác nhau thôi. Tức là allocation của cái department của mình là mọi người muốn chỉ trả cho PhD, còn lại để cho cái tiền dư là ít thôi, chứ không nhiều người xê dịch, nhiều người mua các thứ linh tinh, nó cuối cùng lại PhD ít, mà PhD là cái quan trọng đúng không, nên mọi người quyết là như thế. Thì đã quyết trước khi em vào, nên là khi em vào thì mọi người cứ quyết là funding cái phần allocation mà của em thì là chủ yếu là được 3 bạn PhD cộng thêm với một ít tiền gọi là consumable, một ít thôi. Thế vậy thì
thế mà build attosecond thì hơi khó đấy nhỉ.
Thì em cố gắng cứ cày proposal thôi.
50% là viết
Thế thì quá siêu, quá tài năng.
Đúng, anh giỏi mà.
Không dám em cày proposal thôi.
Thế bên Hồng Kông thì tiếng Trung thế nào? Hay là tiếng Anh hết?
Hồng Kông người ta nói tiếng Anh nhiều không anh?
Em chỉ biết mỗi good morning. Không biết good evening. Không biết good evening. Bên này được cái lợi.
Singapore.
Đúng rồi, nhưng mà nó lại chính là cái không lợi, bởi vì là sau đấy em sẽ không biết tiếng bản địa. Nhiều ở Đức thì là họ cái đợt đầu em ở nó không ai nói tiếng Anh cả, thế là mình toi. Mình mà không mày mò tiếng Đức thì mình toi. Thì là cuối cùng lại phải học một
Đức hơi siêu đúng không?
Không, đấy là lúc đầu thôi, còn lúc sau vợ sang rồi thì
cái Việt Nam.
anh ở bên Hà Lan, bên đấy người ta nói tiếng Anh giỏi, nên là mình cũng không nói được tiếng Hà Lan, bởi vì là không có motivation để học.
Nó cũng có lợi và cái không lợi đấy, nên là tùy từng góc nhìn.
Ok, bao giờ Trung quay lại châu Âu thì hẹn gặp anh em nhé.
Dạ vâng, em mấy năm vừa rồi không đi được conference bởi vì Covid, nhưng mà bắt đầu từ năm nay thì có thể là đi được rồi.
Thì lúc đấy Việt Nam đang định hẹn gặp nhau tháng 7 sang năm, có cái hội nghị tên là Meta Mateo tổ chức ở năm nay, tổ chức ở Paris đấy. Sang năm.
Thế ạ? Anh phiền anh gửi cho em được không ạ?
Có cái hội nghị này đây Meta Mateo Meta cũng to lắm, cái này có vẻ cũng to đấy.
Về vật liệu hả anh chị, hay là
nhiều thứ lắm. Đây mình gửi luôn cái này để mọi người thử nhìn qua cái xem. Meta Conference.
Không chỉ anh Điệp mời
bên cho anh là mấy giờ?
Em cũng mời, nếu mà
bên anh bên là 3 giờ sáng.
Anh Tuấn.
Bình thường 11 giờ đi ngủ, nhưng hôm nay là exceptional.
Meta Conference. Cảm ơn anh.
Meta Material.
Xem mấy cái special session đấy, mấy cái đấy cũng được, cũng nhiều lĩnh vực.
Sư Điệp có làm organizer không?
Không. Mình còn đang tham dự còn chưa được chứ. Nhưng mà đấy mấy hôm trước nói chuyện với mấy anh em Hải Sơn rồi Cường Đặng, Hà Sơn Tùng, mấy đồng chí ở Singapore đang muốn anh em Việt Nam tụ tập tí sang năm đấy, tháng 7 sang năm ở Paris. Còn 2024 thì có tổ chức Olympic Games đấy, nếu anh em tham dự nữa thì
Có cái game nào anh em chơi chung với nhau không?
Ừ.
Ok, cảm ơn Trung nhiều
Xin cảm
nhé,
ơn cả nhà
bài
nhé.
viết rất là hay.
Dạ vâng.
Ok,
Bye.
cảm ơn
Rồi.
Trung,
Cảm ơn
tất
cả
cả
nhà.
mọi
Chúc
người.
anh ngủ ngon. Chúc mọi người
Thank
ngày
you.
mới tốt lành.
Bye
Dạ.
Ok,
bye.
hẹn gặp lại tất cả mọi người nhé. Bye.
Vâng, rồi.
Bye bye.
Chúc anh Tuấn ngủ ngon. Cảm ơn anh Trung rất nhiều bài toán.
Cảm ơn em nha.
Dạ,
Bye
em
bye.
rất là... Chào anh.
Rồi.
Chào anh Hảo, chào Thảo, chào mọi người.